Hello everyone. Today we are going to discuss about opening the device using the device driver. The open call would come from application. The application will give the open call to open the device. How the device will be opened, that will be implemented by us through device driver routine. I had also created a Jamboard for you, which I'll open now. Here is a Jamboard. You can find the link of the Jamboard in the chat. As I can see, this Jamboard is almost full. Yeah, absolutely full. So we'll need another Jamboard that will open today. A new Jamboard for discussion. We name it operations on device. So we continue further with a little review of what we have done earlier. We tried to open the device using the application that will give the open call for the file that will be device file. Every device file is represented in kernel using a struct inode, and every device is represented in kernel using a struct cdev. So here struct inode and struct cdev becomes important for us. So what we have to do is we have to concentrate on struct cdev, provide an interface, because cdev is a device representation, kernel representation, device representation, kernel data structure. So cdev has to be interfaced to the file system at one end, and the cdev has to be interfaced to the device driver on the other end. This is what we need to do, like this. The application will give open call to open some file in the VFS, virtual file system, and the control, this entry, the node, the file system will be created in such a way that this file will have connectors like the major and the minor number connecting to the device driver and the device. Using the major number, it will identify the device driver and go inside the device driver. And there will be open routine that we will implement today, which will help open the device. I have already given you the overview for that. This is the algorithm for initialization function, which we have already implemented. Okay. Now have a look at this. There it is for you. If you look at this diagram carefully, then what we have to do is we have to access the hardware, that is open the hardware first, the hardware that is accessible from across the kernel. And this red line that you see is a VFS, virtual file system, over which is the user space, and under this is a kernel space. The kernel will interact with the outside world using kernel buffers, IO buffers, also called dirty buffers. Okay. Now application will have some user space buffer. The user space buffer that the application will have here, this user space buffer This user space buffer will contain data that had to be moved down to the device. Okay, we'll use MK node, and using MK node we will create two nodes. Before that, we'll do ins mode, and the ins mode will insert the device driver into the kernel. Ins mode will insert the device driver into the kernel. After that, we'll do we'll do MK node, using which we will be able to create a node in the VFS. When the application will give open call, it will not be able to see anything beyond these nodes. So application will give open call, and the file name will be the node, which will ultimately connect to device driver. Normally when we give the open call, it runs some system call routines, but we will map it through file operations, and we'll be able to run our own device driver routine, and the open system call will map not to the system call but to your open device driver routine. And that is where the power lies, in being able to do that. The open method would primarily do these four things: check for device specific errors, after that initialize the device, open and update the file operations pointer, also the file position pointer, and allocate and fill data structure in private data if needed. So these are the four things that the open method will do. And this is the open routine that we have already implemented and mapped. It takes the inode and the struct file as argument. In application, we will give open system call, which will be mapped through struct file operations, and will reach the driver's open routine, where struct inode will represent the file, and struct file p will represent the stream. Struct inode will take input from the file name that we have given, whereas the struct file is the output parameter. Once the open is done successfully and the stream is created between the application and the open file, then the struct file will give parameters of the stream, attributes of the stream. So it's an output parameter. Once the open is implemented successfully, a stream will be created which will be connecting the application and the file, device file, and the stream parameters and attributes will be represented using struct file. We have implemented this. I am giving you an overview. This overview was important. Now, after that, there is a pointer which refers to the device in our device driver. This pointer is a pointer of type user-defined data structure, which describes your device in the kernel. Okay, so we have to modify the attributes of that pointer using container of. Container of is a macro used in our system. It's declared in kernel, which contains three parameters. First parameter is a pointer to the device specific structure cdev from the file system. Second is a data type of the user defined data type structure that describes your device attributes. It is a data type of that type. In our case, we have taken it dev, and the container field is the field inside dev which represents the device specific data structure cdev. Okay, this macro is used to find the appropriate device structure. It takes a pointer to the field of type container type inside the structure of type container type. It takes a pointer of type container field cdev inside dev. It modifies the attributes of the pointer such that the pointer can access the user space buffers, kernel space buffers, IO space addresses, and go beyond the port and access the device memory as well. Now, this pointer is a reference to the device specific kernel data structure cdev from the file system, that is inode. Whereas this is the device representation, user defined data structure, dev in our case. This is called the container, in which you have device access. We describe the device properties and attributes through this structure in our device driver. This container field, this is a device representation kernel data structure, which is CDEV, which is inside dev. This is a reference to the device from the device driver. The container will return a pointer of type dev, that is container type. Okay, such pointer can refer user space, kernel space, IO space, all kind of buffers, and can also go across the ports and access the device memory as well. So this will become very important pointer. Once we have done that we have done in the last class. After that we have to preserve the opened device. Now once we have done this, struct file would be created. Okay, struct file would be created, and inside struct file you will have a pointer called private data that has to be updated. This is the struct file, which is a stream representation kernel data structure. This would have been created after a container off. And your open will have device major and minor number. This has to be preserved. Step number 8b. This has to be preserved in private data field, which is a stream representation kernel data structure, which will tell the struct file that it had to connect with which device ID with which major minor number. So in the private data field, we'll have to keep the device access. Right now the device access is, if you look at the open routine, right now the device access is through this special pointer, which is capable of pointing to user space, kernel space, IO space, and device. This is the opened device. This LDEV is such that the LDEV that is returned from container off. I'm going to talk about this in the next Jamboard screen. Little bit information about this. I'm going to talk about the LDEV that is returned from container of. The return type. We are going to talk about this here. First, it is of type dev. It can point to user space, kernel space, and IO spaces. It points to this new point for you, to memory that is allocated in initialization function. And is pointed to by pointer of same type. That means if you look at your initialization function, in the initialization function you had allocated space for kmalloc, for dev, for n number of devs, we are talking about one of those devs. And pointed to by dev, this dev pointed to a memory, and this memory was supposed to be pointed to by this dev, isn't it? We'll create that memory somewhere here, yet to create. Now this pointed dev, the LDev that is returned by container of, will point to the same memory that will be allocated by this dev. Same locations. Okay. That is what I mean to say. That's why there is no need to do further allocation malloc for this. Now, according to the next step, we have to preserve it. We have to preserve the device, opened device, and we have to make an entry in struct file for this. So we have a pointer of struct file already here. File p points to a field in struct file, and the field is called this. I'll show you. You go to user, src, kernel, appropriate Linux version. Inside this you go to include. Inside include you go to Linux. Here you have fs.h, and inside fs.h you'll find struct file, which is stream representation kernel data structure. Inside this struct file you will find a field called private data, needed for terminal drivers and maybe other drivers. Yes, we are using it as a other driver. Okay, inside this we have to specify that we have to preserve the opened device. Okay, inside this, so we'll preserve it like this in the private data field. LDev. Now the LDev is preserved in private data field, right? And now the device will be preserved until unless the application gives the close call and destroys the stream. The next step in device driver development is check the access mode. The application would have given the access mode that the application that the application has opened the device in read mode, write mode, or some other mode. So let's go to application, and in the application we have implemented open device routine, and inside the open device routine we have specified that the device is opened in which mode. So the open call, if you look at the open call, where is the open call? Here is the open call. We have specified either read mode or write mode. So if in case if it is a write mode, then we have to take additional steps in the open routine. Write means you are going to write into the file, you are going to provide data to the device. Write means you are going to provide data from the beginning of the file in the device. If not beginning, then it would have been append mode. But as it is not append mode, it is in the open mode only. That means you are going to write into the device from the beginning of the file, device files. Therefore, some additional operations has to be taken care of. Okay, we have to check if the device is opened in write mode. If the device is opened in write mode, this is what we have to check, and this will be checked like this. If you have to check AO_access mode in the flags. File P points to F_, flags. Okay, now this f underscore flags is a field here, f underscore flags. I'm talking about this field in struct file. Now this f underscore flags is something like this. It's a 32-bit flag. Out of these 32 bits from here to here, out of these 32 bits, there are some 3 bits that we are concerned of. These are file modes. Okay, these 3 could be read, write, open, append, create. Various other modes are there. So what we have to do is we have to provide the mask. Okay. We have to mask all other bits of flag and make only these 3 bits considered. Okay, you have to make only these 3 bits considered and nothing else. Okay, f underscore flags with 32 bits out of 32 bits, you have to use only these 3 bits. Okay, so how to mask it? Flags should be logically ended with o underscore a double c mod or mod e, something like that, mod e. Okay, after logical ending o underscore access mode with flags, you will be left with only these 3 bits. Now you compare these 3 bits with write only flag. Okay, so what you do here is this: logically and, not bitwise and, logical and flags with o underscore mode. It leaves only 3 bits for you to consider. Okay, then compare these 3 bits with o underscore bits with O underscore WR only to determine that the device file was opened in write mode. That's it. Okay. So that's what we have done. If the device is open in the device is open in the write mode, then we have to trim the device. We'll have to call a function trimDev, which is nothing but a user-defined function. So let me tell you about trimDev first. Now, there is a declaration.h file that we have created, in which we are creating giving the declarations for each and every function that we are using in our device driver. That will include trim dev also now. What will you trim? You will be trimming device, and the device is represented using dev pointer. Yes. So this is what we have to call it, trim dev. And ldev, which is returned from container of, will be considered for trimming. Trimming is like trimming hair, means trimming it from the end to the beginning. Here also you will be doing trimming, and you will be trimming from end to beginning. The trim dev may fail or succeed. I'll tell you about trim dev later on. It may fail or it may succeed, so we'll check the return code from the trim dev. I'll tell you later on next how to trim what is trim. Okay. It may fail if the return value is -1, then it's an error. Here you'll say that trim dev failure is not trim underscore dev. This is trim dev. We will say that trim dev function failure. Okay. And then you go to out, where out you'll jump to out label, and out label will report the error and end of function and proceed further and return -1. Trim dev has to be implemented before we do anything else. Trim dev. Okay. Here is trim dev implemented. The argument to trim dev would be only struct dev, dev pointer. Formal argument dev. That's it. We won't do anything here as of now. Okay, we will just return 0. What has to be done in this is pending for now. Okay, now what we'll do is we'll save everything and test our driver for whatever we have done till now. Is it done successfully or not? Primarily, we have to check this. We have to check if the device is opened in the write mode, and we are testing the write mode successfully. Thereby we will be calling trim dev. So is the trim dev being called or not is what we are going to check now. Okay. Let's check. We have a new file called trim.dev. So we have to modify the make file and add trim.dev also here. trim.dev.o. That's all. Now we have a test script. Yes. Initialization function में तो हम we are not initializing the function pointers. We are not initializing function pointers. We are the initialization function here is for registering, allocating, and initializing the device, not for initializing the function pointer. That was the case when we were doing applications. So test script menu, one is check-in. Okay, I'm not giving comments for check-in. Checkout for build number 2. Number 3, build the driver. So driver is being built now. And the driver is built successfully. See, we took a little time to create this script, but how handy and important this script has become for us now. Test script. Number 4, insert the device driver. The device driver is inserted in the kernel, and this is the output of the ls mode, which gives you the list of modules in the kernel, and there is your device driver sitting on top of the list. This is the output generated through /proc/devices, which displays the device table, and here is your device table entry for your device driver. Enter major number. What was the major number in our case? 238. So we enter 238. Okay. Now this is the list of modules stack. The module stack at the top you will see your device driver CD150, its size, and it is being used by how many entries in the kernel? 0 for now. This is the output of DMESG, which says that you have registered driver with major number 238 and 20 devices listed minor number 0 to 19. Then we'll use number 7, test with application number 7. So application is compiled, and there you see the device driver entry using mk node is created. Hyphen the C on the leftmost column says that it's a character device. This is the major number, this is the minor number. Okay, created on this date, and this is its name. Enter. Application is built successfully. Do you want to run application? Yes. Okay. Number 1, open device. Enter. Please give device open mode. O_WR only. Please give the device name to open. CDD150. This is the name that we gave to the file in the file system. Then it says device opened successfully, FD is equal to 3, and let us check what happened inside the kernel. The control went to OpenDev, and from OpenDev it went to trim.dev. The fact that it is able to go to the trim.dev explains to us that we are able to check the write mode successfully. Okay, so 2 for close. Enter. You see the release dev is also invoked, and then we exit the application out of here and remove the driver number 5. Device driver is being removed. Check must be done. 238 is gone. Yes. And the cleanup function was invoked successfully, and the device driver is removed. Then we do number 6, check out for development. Our device driver is checked out for development. Exit the test script. How efficient this script has made. All the hard work that we had to do again and again and again has been automated by this script. Such an important script it is. Okay. So this CDD150 was created on 2nd of April, I saw just now. This is not right. It should be created every time the device ever inserted new. So slight modification has to be done in the test script, where we are creating MK node. Okay. This MK node should be destroyed if it was already created, and it should be recreated. Now this MK node could be destroyed using RM MK CD150 unlink CDD 150. So if it would have been present, it would have gone now. It would go. We can also put this in clean if okay. Forget it. That was more than sufficient. So from next time onwards, it will be destroyed and recreated. Fine. So this was trimming, all about checking the access mode and trimming. We have done that. So the general things that are required in opening a device through Open Routine has been implemented, and there is nothing more that we have to implement as of now. There are more steps that has to be taken to open the device, which are hardware specific. The common things which are supposed to be done inside the kernel to provide the mechanism called opening device has been implemented for character devices. Few more additional steps could be required. That will vary from hardware to hardware. Okay. Now, if you have any question about whatever we have discussed today, you can ask me now.